So my name is Marta García Martínez. I'm computational scientist at Argonne National Laboratory. And today I'm going to introduce you to Aurora. I know that a lot of you are already running on the system, but we still have some who are just joining. So making sure that at least the minimum commands or the onboarding happens the easiest as possible. So let me click on next. Comparisons in general sometimes are not good, but it is important at least to know what is available at least from the Department of Energy. And today, one element that I wanted to raise is not only the diversity that you see between Aurora or Frontier in the kind of programming models that you use and the hardware that is behind the scenes, but it's also in the number of devices. Aurora recently went into production January 27th, for those who are part of the INSA and ISP, you know how hard it was to reach this point. And it's one of the systems where those who are interested in scaling very high node counts, you don't have as many devices as you have in the other top 1 and top 2. And even these devices, you can, as we can show you later, you can obtain or divide into the stack level, the slice level, and the CCS level. And you can even multiply this number by 96 if you want per node processes, MPA processes or ranks. So it's a lot of, it's a huge machine, very complex. So I will share some information that is available on our website. Please, at any moment, interact with us. We are here to help you understand the system as it is. Those who like cars or those who like bikes or computers, obviously, try to make sure that you understand every difference from the machine that you are running now, because it's important to transition the best possible and use the nodes and the whole system the best possible. As you probably are aware, well, this is new. It's a new picture. We are covering now the first row of Aurora. I know that you have a visit on the first day. For those who will be in person, is on May 20th. You are going to visit you are going to have a tour. So you will be seeing this view of Aurora, where you have the first row of the racks in what we call the Aurora reveal, which is pretty impressive. There is a terminology that changed over the years of conception of the machine. So you probably heard about the kind of CPUs and GPUs. So the CPUs, you may have heard that they are Sapphire Rapids. Now officially they are Intel Xeon CPU Max series. And for the GPUs, you may see us interchangeably saying or the data center GPU Max series or the Ponte Vecchio, PVC. Okay, the system is very powerful, as we said. You have 10,600. I don't know, can you see my mouse, making sure that the mouse works? Okay.
Yes.
Yes, okay. 10,624 nodes. And in the previous slide, multiply by 6 for the GPUs. But even you can go, as I said, higher and higher. So you still have the possibility to make sure that you use the CPUs and the GPUs the best possible. We have, as seen on Frontier, we use a Slingshot 11 for those who are coming for the systems, or for those who are coming from, like I think there is another Intel GPUs machine called Down in UK. So make sure that you ask us about the differences in bandwidth and node performance, in system performance, and the speed of the network. Anything that you need is summarized here. I will not go into the detail because we will have some slides, and it will take too much time to go into all the details. So keep note of everything that changed, that has an impact, that you want to know more. Today, I mean, you can put it in your favorites or a bookmark or an easy way at least to know how to read documentation because you're going to digest a lot of content in the next days. So we have everything that is available in our alcf.anl.gov portal, and then the Aurora. This is, you go into machines, Aurora. So is one of the links that I posted in the chat, and you have also in the general channel on the Slack. This is the main link where I got the examples that I was sharing today. Briefly, again, there are other examples more sophisticated in this other link, which is the Insight Hackathon 2025, which I don't know now, you see better. So if you want to follow today, open a terminal. I will not going back and forth between terminal slides, so you don't get dizzy after lunch. I have screenshots. I tested everything this morning. The purpose is to make sure that you can follow, and anything that doesn't work, you let us know as soon as possible, so you can start getting ready for the next days, okay? So these are the main places where you will get the information from today. And let me click here. One note. Aurora is not perfect. We still have things to understand. And there is a known issues webpage where we are trying to keep track of what is going on. So I'm sure that all of you will have challenges and you will face that you will face during this hackathon. Anything that you can help us document to make sure that we follow up and solve, please take a look at what is already known as a problem. And then if it's something that happens to you and is not listed there, please make sure that you help us report it too. That way we can fix as much as possible. I'm a visual person, so I like a lot of images, and especially I like to understand the machine on itself. You probably have seen this image before with the red and blue tubes. These racks are similar on the outside, let's say, as those on Frontier. You take a picture of one rack on Frontier like this. These were still not populated, so it's an old image. But here, each one of these are one of the compute nodes, what we call exascale compute or blades, one of the blades. And eventually the difference that you have with Frontier is each node will have, each one of these blades will have 2 nodes. And we have one. So each rack, like you see, the front and the back is representing 64 of the nodes. For some of you, that will be important. For others, maybe less of an issue if you can run anywhere. But if you are trying to reproduce a problem and you want to specifically submit something in a particular location of the machine, that can be possible, okay? So like to reduce the source of problems that you can find, that's a way. And also you are studying MPI or your global communications or MPI and your communications, there is also that option. So at least start physically visualizing the machine as a set of racks, slots, chassis, and obviously the nodes and everything that is in between. Okay, so I will show you some of the other pictures, especially this is very useful for me. I hope it will be useful for the audience. It's a global representation for internal purposes, but right now I want you to understand that when you will see the machine in person, you will only see the first row, which is this one. And this is, in general, the racks, where you saw the Aurora picture, that's the set of racks that you see. Behind the scenes, you still have 166 cabinets or racks. And each one, as I was saying, with 64 nodes. And those nodes are also divided in sections. So the representation, when you log in, we will be doing a logging in, or at least you will see if you can do it in real time, following the directions in the slides, that's perfect. If not, at least do it in the next days to make sure that you see. When you are gonna request an interactive node, you will land up on something that is like this. So every single section has a meaning. So the X is gonna represent the racks. C is gonna be the chassis, as you see here. S is gonna be the slot. So the slots are represented here. The chassis is from 0 to C7. So if one day you are interested in understanding better what is happening, this is important. In any case, for us as support, anytime that you have a problem, the first thing that we'll ask you is the job ID, so we can track this information and know where your job was running, and to see if it's a particular problem with that node location or something else. So it's important for you at least to know how to understand the machine with these images, hopefully. Next slide. At the node level, we have, as we say, a lot of pictures, a lot of information on the speed of the interconnect. And we have here the 6 represented, the 6 GPUs. This is the normal 1, 2, 3, 4, 5, 6. With each one is going to have like the 2 sockets. This is the representation, also the very nice representation of the CPUs. And this is the reality. This is the exascale compute blade that has the 1, 2, 3, 4, 5, 6 GPUs, and the CPUs that are here. You will see that too. That is one of the nice things of the in-person event, is that you will be able to touch one of these ECBs that is pretty heavy, by the way, and you will see the handle and how it fits into the machine. So just node characteristics summarized here for you to remember, especially in comparison with other systems, is, as we said, 2 CPUs. Each CPU has 52 cores. Okay, so still have a lot of cores power there. And the GPUs, you have 6, as you will see in the representation of our website and in this image. And then everything that corresponds to how you are gonna move things around. What are the kind of links that you're gonna have, PCIe or X-Link, if I'm going from the CPU to GPU or the internal GPUs. So all these details are summarized here. Again, we won't go too far, but if you can extract information, if you're especially gonna be using the profilers, that is very useful. That way you can compare, am I as fast as I was on the previous system? Am I running, am I using the whole bandwidth or not? Okay. If we go into the small, like another physical representation, one important element to consider is that how you can extract the maximum power or the performance from the GPUs, but also from the CPUs. Okay, so at the end of the presentation, we will go over CPU bind and GPU bind. That way, for some of you might want to use something generic, but if you want to list explicitly and do the binding, it's going to be probably faster. There are some things to know that I will present later, but just to have a visual understanding of how much you can get from this machine. As we said, we have 2 sockets in each one of the nodes. This is a easier representation than just visually seeing the real physical node. And you have to consider that. So socket 0, you have to know also what are the GPUs, if you're interested in understanding better your performance, what are the GPUs in that socket and what are the GPUs in the other socket, in case you want to extract from MPH or, as we said, the communications, a faster performance, okay? So let's first start very simple. I'm assuming that everybody was able to log in, that all of you have a username that are part of the, as Jesse said, the GPU_hack project. And as you log in like in this, if you have used other machines at Argonne, Polaris, you will do the same. It's Polaris at ALCF. For Theta it was Theta or Mira. So that is the easiest way to run. You will need your token. I personally have a physical token still. Most of you probably will have that with your device. Make sure that at least before the end of the day, if you're new, especially, you try to log in, everything that works. And we're going to use 2 spaces. I mean, you can, in principle, technically for these simple examples, do it in home. But if you want, and you are supposed to be part of a project for this event, you go to the project directory and then perform your test there, okay? And there is another space I didn't put at the beginning that is useful, especially if you are a PI and you have an allocation. This is my ALCF login. And in any case, one thing is where you land, like the login nodes, and then you want to know also the quota most of the time, especially you have huge allocations, huge simulations. You need to know the quota. So my project quotas gives you a list of the projects that you're part of and also the information about the quota. You have to make sure that you have enough for running. I don't think it should be a problem for this test, but in the future, make sure that you estimate appropriately how many terabytes do you need to make sure that you ask for the right amount of space. Well, my ALCF is also a way to have an information of how is your allocation evolving. You will see the consumption there. And if you have any need or special need or request, we are always there, support@alcf.anl.gov. Send the email and we will evaluate your request. So today, try to reach your project directory, okay? And let's get us started. As Jesse was mentioning this morning, there is a project name called GPU_hack, and then a queue that has higher priority, which is GPU_hack_prior. Try to use this if you want to test in real time. As I said, to make sure that everything will work, we test everything the day of the event. We don't have, so in general, we have a visual representation of some of the systems we call it Gronk, the Gronk collator. We have that for Polaris. We don't have that for Aurora yet, but if you want to take a look at what is running in the machine, this is a very easy way to find that information. You can also see what are the reservations available. But for today, remember this line. We can post it in different places, so to make sure that it's easy for you to retrieve. But if you type this command, you will end up, since we are asking, and I will explain some of the commands later, we are asking for an interactive node. You write this down, and then you will end up, as soon as the machine is available, you get a node. As I presented before, these nodes have, when I was landing this morning, 4516, that's the rack. And then with chassis number 2, and then it was the slot number 0. Okay, so you will see something like that when you log in. Your environment. We use modules. I don't know if you are coming from an environment where you use modules. Probably yes. So that simplifies the transition. So in this case, I have some outputs in the next slides. But here right now, try to type module list. It's supposed to give you a set of default modules. Not all the systems may have that, so it depends. For example, if you log into JLOC, which is a different structure at Argonne, you don't have anything by default. So make sure that at least you understand what is available when you just jump in one of the login nodes, okay? And then what is available in the sense that what is listed for you as default in case you need to change. And then what is available, you do module avail. One set of modules that are by default not visible, but you just need to add that. I personally have it in my bash RC file, or export in your scripts the soft module files, or just module use soft module files. It will add a set of modules that may be of interest for you that are available on the machine. Because you might need, for example, to use and load CMake. Okay, you don't need to build that on your own. Some default software is a part of a SPAC, for example, and if you have module use soft module files, you will have that as part of the list. So you just need to module load the module that you need. We don't have everything we are building. So if there is something that is extremely important for your team that you want potentially to have in a module, maybe we can evaluate if it's possible to add it, or if it's part of a SPAC. SPAC is a huge software package manager, and we are trying to get it operational on Aurora, so you will see that not everything is there, but we can help you at things. And this is just an output. If you are on the system, as I said, module list, it will give you something like this. You have one API loaded by default, so you have the compilers there. And if you need to load, you will see that something is added. Some models have dependencies, so when you add something, it might take back and use a different version. So make sure that you understand what you need in your environment before starting building and compiling. And just as I was mentioning, if you do module avail, you start seeing all the modules that are available. For example, those who are interested in using PETC or HDF5, ParallelNet CDF, SuperLU, for example, Darshan, that's for profiling IO. And even we have this morning, there was a thing with GeoPM. So you have a GeoPM module there. And just let us know, as I was mentioning before, what do you need and if it can be used. There is also a version for Hyper, although personally for a different project, I'm building Hyper myself. So sometimes you will need to build on your own because you need specific options that are not available, but we can consider eventually, if it's easier for you, introduce other options too. Let's get started. So I was mentioning, I'm following what you will have online, so it's easier for you to go step by step if you cannot now, but then the next days. So I'm going in this particular space, ALCF beginner's guide. That was very low level. And then I'm going into the section where we talk about the schedulers. Okay, so you need to know these basic commands to submit. And for those who have been running in our systems before, well, this is a lot of repetition, but at least make sure that today we try to submit with QSub dash capital I is going to get you the interactive nodes. So if you submit this, you are supposed to get a node, and then we can start testing. If you would like to follow directly now or later, we put some examples in this GPU hack ALCF training examples space. Those are coming from this GitHub cloning. You can clone also directly from there, but at least you don't need to copy them because they are there. Make sure that, as I will show in the slides, that you change the mode because these, for example, they are not executable. But anyway, these are very simple examples for you to reproduce. You will see that it's very easy to follow. If you need to have information about what is in the machine, like the GPUs, I'll have a screenshot later, but at least, okay, let me go back. We can load, you need to load this XPU SMI module, and then type discovery. That way you will be able to see the output of the GPUs, the information that you have, and eventually compare if you want with other systems. Okay. And again, I will have a screenshot later. So let's get started. You're going to submit a node. You can do it interactively if you want to do it there, or you can do it also, you can run with QSub, normal submission, and copy this file if you want. It's in the examples location that I was mentioning before. And this is the hello world. This is a simple CPU case. So there's not too much. It's just to get acquainted with what PBS has to offer. Most of the time, this is easier if you have the information in the scripts, but you can override when you submit the QSub command, you can override whatever is inside the script. So this script has, for example, the debug queue, and there is no specification of project name. So you can leave it as it is or change it directly there, or in the QSub command, we can override that, okay? So today, just make sure that you can keep the name of the file, or you can name it as you want if you want to play around with it. And a note eventually is that it's easier if you create a logs space, a make dir, a directory in where you're going to keep your standard output. But feel free to do as you prefer, and we can help you also get the best out of all the PBS commands that are available, okay? Important element, I mean, you should be aware, but make sure that you don't forget to put the file systems. You won't be able to run without that information. So we need the home, I mean, especially Flare, which is the file system that you're going to be using on Aurora, and your home if you have something there. So it's a good practice to have all these elements here. As I said before, so this is an example where you are just submitting in one node. You can specify more information in this select command, and you can specify exactly, for example, the tier in where you are running, or if you just want to ask for a tier in which your run is going to run in a particular rack instead of be spread out in multiple places all over the machine. Okay, so to run a simple script, we do qsub and then the name of the script. If we want to override the options, we will have to put qsub -a, project name, -q, in this case, GPU_hack, and then the JavaScript. And what we'll see is what is supposed to be happening inside the script. Okay, and again, that was a very simple case. What do you do when you submitted the job? You want to know if it's running or not, what state it is. So this is simple qstat-u and your username. I personally have an alias qs, just here is qsme. It's much faster because you're gonna probably keep checking frequently. So it's easier to get that into your bash RC2. You will probably have to kill sometimes your job. You can move it also. You can do all other operations, but if you need to delete the job, qdel, qdelete. Sometimes it doesn't kill. You have to stab it harder. So it's -w force. So if you have issues one day killing the job, try with qdel, if not qdel -w force. And if not, please reach out to support, okay? Right now, I think probably we were doing better in killing jobs in the sense that it was working, but sometimes it gets stuck. So let us know as soon as possible. And then, as we said, your job is supposed to have an output. Most of the time, if you want, it's going to have the job ID. For us, it's very important to keep that information. So at least if you change the name of the error and output files, at least find out a way for us, for you to find that information if you encounter problems. Okay, so that's very important. And again, in the next examples, I put the results in these logs files, which is in my personal directory. You might have that too. So if you need to check where is the output and if it went well, that is where you find it. So this is just an example of the screenshot that I got this morning. You should be able to get this today. As I was saying, you have the XPU SMI command. If you load the module, and you will see we have the 0 to 5, all the 6 devices, GPU max, this is the PVCs, all the 6 PVCs, the physical PVCs. And then how to submit a job, making sure that you specify that. GPU hack and the priority and the logs. But this is just for your reference. And if you reproduce the first example, which was very simple, you will see the hello world 6 times. There are a lot of commands that can be very useful. Even for those who are experienced in our systems, is always a good reminder to go and check back. So we have this cheat sheet. One of the elements that is important, in addition to qsub, and to know how to evaluate the status, you might want to know more information. So qstat allows for some options, and you might want sometimes to submit but keep on hold. So there is a way with this hold a job and then release a job. you might want to prepare the job and then submit it, and then but not I'm not sure yet. I still need to figure something out based on the previous job or something like that. So you can hold the job and you can release it. At least you you don't waste some time but in the queue. However, when you are on hold, you are not increasing the score. So as soon as you start running, you want to make sure that when you submit, you get the fastest possible to the beginning of the queue, so you run. So one of the elements that is managing the scores is the size of the jobs and the projects that you are in and the time you're asking. So if you are preparing a campaign, it's useful to understand how dependencies work, and we can dig in more separately if you want, but at least you inherit the 50% of the score of the previous job if you have a dependency set in place. Okay, so make sure that let us know what you need and we can help you understand how to do it better with the scheduler. And okay, you can also receive notifications, this capital this -M, to receive an email. I personally, since especially when you are testing or debugging, I don't have this on, but if you have a campaign where you want to know when your job is running, that's very useful. So if you have time, slowly take a look at the options that QSoup provides. It must be some of them are very useful. You have also variables, environment variables that are inside the script that can be used. For example, I personally put in the log file. I always try to have the node file or the job name, obviously the job ID. In addition, and inside, making sure that you have work there. Instead of just pointing to a particular place, you might end up having your log files in home. So they are available to you. Experiment with them if you want these days, and as I said, ask us as many questions as necessary. So let's start with, now I'm going to the next section, which is the compilers. I'm assuming that you were able to log in, that your project is working, and that you test it minimally. So you probably need to, next step is to compile. And you will have presentations, I think Colleen and Thomas are presenting tomorrow also for running and building. So this is very relatively quick, high level. I want to make sure that I'm not running too much out of time. Okay. So what are the compilers that we have? We have for C, C++, and Fortran. And as you probably are aware, we are encouraging teams use SQL. We have OpenMP target. And we have obviously MPI, which is Aurora and Pitch behind the scenes. So today, very simple test is one of the examples. We have some wrappers that you can use in your scripts. Every time that that we mention the compilers, reminds me the idefix, Asterix, and Obelix. So for C compiler, we have ICX, C++ is ICPX, and the Fortran compiler obviously is IFX. And if you may be using a particular one or a mix, make sure that at least recover this example, which is one of the ALCF training / examples /01 examples C++, which is one of the files that is available, and then try to compile. You shouldn't have any issues performing this operation, and then try to execute if you are in an interactive node, very quick. But this is just a simple test with CPU, okay? So we just to get us started to make sure that everything is working. And this is just the information that is inside the file. So it's not very complicated, just writing hello world. If you want to go now and compile for the GPU with OpenMP, and we have the same set of information for OpenMP and SQL, two things that are important is the choice of compiling for when you want to have a GPU enabled application is to compile your kernels, your GPU kernels at link time or at runtime. If you want a link time, it's what we call ahead of time, AOT compilation. If you want to compile them during the runtime, is what is called just-in-time JIT compilation. So you will need, if it's OpenMP or SQL, a set of commands at compile time and linking. Okay, so make sure that you have this in your scripts, in your command line to build the code. What is ahead of time different from JIT? As we said, one is trying to compile that when you are linking. So if you are gonna create a executable only once, for example, and then you are gonna run your campaign, most of the time you don't change what is happening, then you're gonna save time because you are not doing the compilation every single time that you are running. So most of the time what you see is or what we recommend is to compile ahead of time and then use your executable because you're gonna save time running. However, if you are in an environment where you are changing a lot, still testing and building your application can take a lot of time. We have seen applications that can take 1 hour or even more. So if that is the case, then you can compile with just in time, and then it will be faster. Your compilation, it will be slower, your runtime, but since you are trying to figure out, especially compilation changes and running, it might be an option for you. In any case, whatever you decide, make sure that you have the appropriate compile and link lines that are added to your files, to your scripts. This is just the example of OpenMP that we have available on the examples that we share. If you type this command, and if you type the second one, this is what we see here. I was in my test, was performing these operations. This is the expected output in the screen that you should see. Some codes, they have issues with the double quotes. So personally, for one code that I'm working with Chuinta, we have to put these commands in a separate file and then point to that file. So if you have issues with the double quotes, just let us know, and we can guide you there. This is the same thing. It's just making sure that you can submit. So if you want to double check before running, because eventually you are making changes and you want to know for your publication what is the exact compiler, as you probably all know, which ICPX is going to give you the one that you're using, and then the version. Sometimes you want to make sure that you specify, okay, well, I'm using this compiler. Right now, this is what everybody should be using. This is the default, and let us know if it works, especially, okay? Today, if you want to try to execute this for the GPUs, just run the command. Again, these two elements, -A and -Q, in the QSUB line are going to override what was inside the SH file. Okay. In the SH file, I have debug and we have no project name. So make sure that, for me personally, it's easier to document myself better in the script and make sure that I use the right one. But sometimes you need that flexibility. So it's up to you. But let us know if something needs to be change for your needs or added some of the elements. As I was mentioning before, the outputs, if you are performing some tests now in real time, will be, if you created the directory, it will be in the logs, and it will have the job ID and the host name. If you want to keep the host name, that's fine. If it's too long, feel free to override, but at least make sure that you have an output and an error. And then make sure that you're supposed to see what we see here. Okay, so if you don't see that, let us know. Same thing, we talk about OpenMP, an OpenMP target in this case, and then SQL. It changed a little bit the way how the command line, so it's fsicle. Before, if you remember, it was fi openmp, and then we have f openmp targets. So in here we have fsicle targets, so it's almost the same, but make sure that you adapt depending on what you need. If you are compiling with SQL and openmp target. I will not go into this detail. This is exactly the same example, but with SQL commands and the SQL C++ file. So you will see, in principle, the same output. And now going back eventually to the importance of understanding how to run and how to use the CPUs and the GPUs the best possible. You have the options when you have this MPI exec command, which is you're going to submit your job in these lines. You're going to specify how many nodes you use, how many ranks per node are you going to use. And you want to make sure that also you understand how many the CPUs that you're going to use. So you can go today, for example, by default, you can put CPU bind depth, which is going to be using the CPU cores. And each MPI rank is going to be assigned to consecutive set of CPU cores. But the more you practice, the more you understand your application and what parts are done on the CPU and what parts are done on the GPU, the better you will be able to use this 52 cores times two for the hyperthreads. Okay, so there was one of the representation at the beginning, color coding, that I will have a next slides, is just understand how you bind your CPUs to your code and how you bind your GPUs. It's gonna get you better performance. So you can list, well, this is just a representation of the sockets, and it tells you that the NUMA domains, in this case, is that for node 0 and node 1 for the CPU. So it's from 0 to 51. And then the second one is in the second NUMA domain, so the second set, let's say, for 52 to 103. And then it goes like this. So understanding how this is impacting the how your data is going to move around is also very important. So that's why you will have probably to test as much as you can, and let us know if you have questions about this and how to tweak it better. So this is a recent email that was sent. It was on March 31st. So those who were part of the system before probably remember and notice. If you're new, I wanted to make sure that is mentioned. It's part of our online documentation, but it's just that initially all the cores were available to be used. If you want to specify a binding and want to say, I'm going to run my CPU commands in this row, for example, or in this set of CPUs or cores. Now, these two and these two, like 052 and 104 and 106, are not available for users. So make sure that if you recover a list command, like a CPU bind list command, make sure that you understand how things are placed to ensure that you don't use the ones that are not available. It's going to tell you that they are not available, but I mean, that saves you a little bit of time. So you can do it that way. But the more you can share these days about how you are running in other systems, in comparison, for example, with the GCDs on Frontier, if you're running there, the better we can help you understand how to extract the maximum performance of the code. And same theme, I want to make sure that I'm not too late. Okay, same theme for the GPU affinity. Remember the initial images of the system. You have to picture yourself in each node almost, and each node in the whole system, especially if you're gonna use a lot of nodes, how things are gonna impact on your performance, but also at the node level. So start experimenting a lot if you can at the node level, understanding how you can tweak and tune these GPUs and this CPU binding. So to extract the maximum performance at the node level and then scale that up. As we were saying before, you have 6 GPUs, so the physical GPUs, but those physical GPUs, they have 2 sockets. Obviously, they are in 2 sockets, so they have the slices. So in general, you can span in 12 MPI ranks per node. That is a normal test that if your application is not too memory greedy, let's say, you probably can try it. But you can go further. You can go at the level of the CCS, the compute command streamers, and there are some cases, some of the samples of the CPU type. It has a different name also on the machine. There's set affinity. You will see it in the helpers scripts. In that examples space, you have helpers scripts, and in there you have some examples to extract the information of the GPU and go half of the GPU tile of the stack. And you can go even deeper. So it might be that your application allows to go at that level. I personally tested with a code called Uinta. We were able to reach 122,880 XC stacks, and we tested a lower scale to go and even go even farther, divided by 8. And you might be able to exploit per node 96 processes or MPI ranks. So that is important for you to experiment these days, okay? Again, the more you know about your memory consumption, the more you evaluate with the profilers that will be presented, the better. Okay, but at least this information is available, and we cannot go too much into detail, but we can help you understand how to extract the maximum performance during this period of the hackathon. And this is a very nice, well, I posted the link here. It's a very nice representation. It's a different graphics for the machine, but you have to always have a picture in mind so you can understand how far can you go. Because even at the level of the slices, you can even go at the level of the, what we call it used to be called executing units, and now it's vector engines. And you can go very deep. Each one of these ones, tiny little squares here represented. So hopefully you will be able to get the maximum of the machine, and even at the level of, if you are using OpenMP threads or any other kind of structure, that it can be possible. We don't have a list of last simulations, but we have been running very high node counts and almost up to the full machine, as I was saying with Uinta. I think it was 96% of Aurora at the time. And this is my last slide. I don't know if you, when you were a kid, I used to read some of those Choose Your Own Adventure. They used to be in Spain also available, in which you decide where to go. So I reach a point in the book where you have to decide. So this is the moment of deciding, or at least one of the moments. We want you to explore as much as possible, but find out what you want to explore. You want to explore these days the node level because you know better how to scale further. You want to understand better how to run in a particular chassis, or understand the impact of the transition of the data index, EasyLink. Anything that you might consider, let us know. But you have to choose your adventure today with Aurora, and hopefully we can help you scale as much as possible.